Section: Introduction. In this section, we discuss the design of a powerful neural network architecture, which has been a key goal in machine learning. We highlight recent advancements in foundation models, particularly the effectiveness of transformers as a versatile computational framework. Their adaptability and scalability have led to top performance in various fields, such as natural language processing, visual modeling, and more. Transformers process each token through two main interactions, one with other tokens and another with the model's parameters. The attention mechanism plays a crucial role in facilitating interactions between tokens, enabling the encoding of multimodal data into a single token sequence and capturing complex relationships. On the other hand, interactions with model parameters rely on fixed linear projections, which can limit scalability. As we increase the model size, we often need to retrain the entire model, leading to high resource consumption. To address these challenges, we introduce Tokenformer, a new architecture that enhances the flexibility of token parameter interactions. This allows us to scale model parameters incrementally and reuse previously trained models, significantly reducing the training effort. Tokenformer unifies the computations of token-token and token parameter interactions entirely through the attention mechanism. Our token parameter attention layer can handle a variable number of parameters, improving scalability. We extend the transformer architecture by maintaining the computational patterns between input tokens while reformulating linear projections using a cross-attention mechanism. For projecting features with specific input and output dimensions, we use two sets of parameters, each consisting of learnable tokens. In this setup, input tokens act as queries, while model parameters serve as keys and values. This design allows us to efficiently expand the model by adding new key-value parameter pairs. Our model can be scaled from 124 million to 1.4 billion parameters, achieving performance comparable to training from scratch while saving over half the training costs. The main contributions of our work include 1. Proposing Tokenformer, a fully attention-driven neural network that treats model parameters as tokens, enhancing the flexibility of token parameter computations and achieving competitive results across language and vision benchmarks. And 2. Enabling natural scaling of our model by progressively adding new key-value parameter pairs, which reduces training costs compared to traditional methods. We also review related work, noting that the transformer has become a foundational architecture in deep learning due to its adaptable attention mechanism. While it effectively manages interactions among input tokens, it lacks flexibility in handling model parameters, which are typically processed through fixed linear projections. Our goal is to restructure these interactions by creating a fully attention-based network that integrates both token-token and token parameter computations. We recognize that large-scale training is crucial for developing powerful foundation models. Simpler architectures, when paired with larger datasets and increased model sizes, often outperform more complex algorithms. Scaling data is generally more cost-effective, allowing for continuous integration of new data without altering the model's architecture. However, increasing model size can be costly and often requires retraining from scratch, raising expenses significantly. In terms of model reuse, traditional methods often involve initializing larger models with pre-trained smaller ones, which can disrupt the smaller model's established distribution and risk losing pre-trained knowledge. Our approach allows for seamless parameter scaling while preserving the integrity of the existing model. In the following sections, we will revisit the conventional attention mechanism, introduce Tokenformer as a scalable architecture centered around a flexible token parameter attention layer, and detail the incremental scaling of Tokenformer. Section Summary. In this section, we introduce Tokenformer, a novel neural network architecture that enhances the flexibility of token parameter interactions by employing an attention mechanism for both token-token and token parameter computations. This design allows for incremental scaling of model parameters, significantly reducing training costs while maintaining competitive performance across various domains. Section: Preliminaries. In this section, we discuss the foundational aspects of transformer models, which have become essential in deep learning due to their impressive performance across various tasks. The key to their success lies in the self-attention mechanism, enabling the model to evaluate the significance of each token and effectively capture complex relationships among them. We start with a set of input tokens represented in a matrix format, where each token has a specific channel dimension. The self-attention block generates three components: query, key, and value, through distinct linear transformations using learnable weight matrices. We calculate attention scores by assessing the similarity between query and key vectors, applying a softmax function to normalize these scores. These scores help us compute the output of the attention mechanism, using a scaling factor to address small gradient issues. The final output allows the model to handle interactions between tokens of different lengths, enhancing its ability to process diverse multimodal data, which is crucial for the advancement of AI and the effectiveness of transformer systems. Next, we introduce Tokenformer, our proposed architecture that addresses the scalability limitations of traditional transformers, which often face high computational costs due to fixed token parameter interactions. Our approach, Tokenformer, is built entirely on attention mechanisms. The main innovation is the token parameter attention layer, or potential layer, which includes trainable tokens that act as model parameters. This layer uses cross-attention to facilitate interactions between input tokens and these parameter tokens, introducing a new dimension that operates independently of the input and output channel dimensions. This separation allows for dynamic interactions with a flexible number of parameters, enabling efficient scaling of models without the need for complete retraining. We define the input and output tokens in matrix form, and to implement our potential mechanism, we introduce two sets of learnable parameter tokens for keys and values. The output from the potential layer is computed using a modified softmax operation for better optimization. The attention scores are derived from the interaction between input tokens and parameter tokens, with a scaling factor to enhance stability. Our potential layer maintains the adaptability of attention mechanisms, allowing it to process a variable number of parameters while being independent of the input and output dimensions. We illustrate the overall architecture of Tokenformer, which follows the pre-normed transformer design. The output computation of a Tokenformer layer involves layer normalization and our modified multi-head self-attention and feed-forward layers. For simplicity, we consider a single head variant and replace linear projections with our potential layers. We denote the input to the multi-head self-attention block and outline how token parameter and token attention are handled. Our model closely aligns with the hyperparameter configuration of standard transformer architectures, such as GPT-2, maintaining the same number of layers and hidden dimensions. The number of key-value parameter pairs in the projections corresponds to the hidden dimension, while the feed-forward module uses a larger number of parameter pairs. This design allows us to initialize our model's parameters using a pre-trained transformer, ensuring smooth integration into the existing transformer pre-training framework. Section Summary. In this section, we introduce Tokenformer, an architecture that leverages a novel token parameter attention, potential layer to enhance scalability and efficiency in transformer models by allowing dynamic interactions between input tokens and trainable parameter tokens, independent of input and output dimensions. This design enables the effective reuse of pre-trained weights and facilitates incremental model scaling while maintaining performance comparable to traditional transformers. Section: Progressive Model Scaling. In this section, we discuss our progressive model scaling approach. Our model is well suited for large-scale training due to the flexible design of the potential layer, which allows us to build larger models by reusing parameters from smaller, pre-trained models. To illustrate model scaling, we use a single potential layer. We start with an existing Tokenformer model that has pre-trained key-value parameter tokens. To scale the model, we add new key-value parameter tokens, combining them with the existing ones. This method enables us to integrate more parameters without changing the input or output sizes, improving training efficiency for larger models without sacrificing performance. By initializing new parameters to 0, similar to the LoRa technique, we can maintain the model's pre-trained knowledge, leading to faster convergence. Next, we present our experimental results. We validate our model's ability to expand continuously and demonstrate its effectiveness in both language and vision tasks. We also compare our model to standard transformer models and conduct ablation experiments to assess the importance of each module in Tokenformer. For our datasets, we use the Open Web Text Corpus, which is a well-known open-source version of OpenAI's WebText dataset, containing text from over 8 million Reddit shared documents. During training, we randomly sample segments from these documents. To evaluate our progressive scaling strategy, we establish a baseline by training a transformer model from scratch. We use the AtomW optimizer with a batch size of 512 sequences, each with 1024 tokens. We create two training variants based on the total number of training tokens, one with approximately 300 billion tokens and another with about 30 billion tokens for fair comparison. We then test our model scaling with parameter sizes ranging from 124 million to 1.4 billion. Each scaling iteration uses a pre-trained smaller tokenformer to initialize the larger model's weights. We start by training the initial model on around 300 billion tokens. For scaling, we choose the pre-trained model closest in size to the target. For instance, to train a model with 354 million parameters, we use the 124 million model for initialization and retrain it with a reduced token budget. Our training optimizes the autoregressive log likelihood, averaging over a 1024 token context, and we evaluate log perplexity on the test set. Our results show that our progressive scaling method achieves performance similar to a transformer trained from scratch while significantly reducing training costs. Starting with a 124 million parameter model, we scale to larger sizes, requiring only an additional 30 billion tokens, 1/10 of the cost compared to the scratch-trained transformer. Our model achieves a test perplexity of 11.77 at the 1.4 billion parameter level, while the scratch-trained transformer reaches a perplexity of 11.63 at 3 times the training cost. We present the training costs for each scaling stage, showing that our method is much more cost-effective than training a transformer from scratch. Even when accounting for all scaling stages, our approach demonstrates lower computational costs, validating its effectiveness. Our progressively scaled model achieves a lower perplexity compared to a transformer trained from scratch with the same computational budget, highlighting our method's superior efficiency and scalability. Section Summary. In this section, we demonstrate that our progressive model scaling approach effectively enhances training efficiency by allowing the integration of new parameters into larger models while reusing pre-trained weights, resulting in significant computational cost savings. Our experiments show that this method achieves comparable performance to standard transformer models trained from scratch, but with substantially reduced training budgets, validating the effectiveness of our scaling strategy. Section: Benchmarking of model expressiveness. In this section, we evaluate the effectiveness of our proposed architecture through standard autoregressive language modeling tasks, comparing it with existing transformer-based models. We use pre-training metrics like perplexity and zero-shot performance measures. Our training is based on the PILE dataset, following a specific training protocol. We present the performance of our model, Tokenformer, across various recognized zero-shot tasks, comparing it to leading open-source transformer models of similar scale, particularly Pythia, which shares the same tokenizer, dataset, and training duration of 300 billion tokens. Our results show that Tokenformer performs competitively with the standard transformer, highlighting its expressive power as a foundation model. For visual tasks, we validate our model's expressiveness by comparing it to the standard vision transformer, VIT, which was trained using supervised learning on the ImageNet-1K dataset. We ensured a fair comparison by using the same codebase and hyperparameters. Our findings indicate that Tokenformer matches VID's performance in visual modeling, confirming its capability in this area. We also discuss how transformers can achieve some level of model reuse. The net-to-net method allows for expanding the width of neural networks by duplicating neurons. In this approach, we use the pre-trained weight matrix from a smaller model to create a larger weight matrix for a bigger model. This expansion involves new parameters for the larger model while maintaining the scaling procedures outlined earlier. Regarding long context modeling, we emphasize the importance of efficiently processing lengthy text sequences in large language models, LLMs. The training costs of transformer architectures are divided into interactions involving model parameters and those among input sequences. We note that the computational complexity of transformer models grows quadratically with text length, which necessitates expanding model parameters while managing the computational load of token interactions. Our model addresses this by decoupling the computation cost of token interactions from model scaling, allowing us to increase parameter size without raising the cost associated with token interactions. Our results show that Tokenformer offers significant computational advantages over traditional transformers, especially with longer sequences. We also highlight that Tokenformer can maintain its output distribution when new key parameters are initialized to 0. This feature is advantageous for scaling models to include more data without disrupting ongoing training, leading to faster convergence. We compare the loss curves of net-to-net-based transformer scaling with Tokenformer scaling, showing that Tokenformer converges more quickly and achieves a lower final loss due to its ability to preserve the output distribution during training. In our performance benchmarking on incremental scaling, we progressively scale the standard transformer using the net-to-net approach, ensuring all hyperparameters are aligned for a fair comparison. Our results indicate that Tokenformer outperforms the standard transformer in scaling. Finally, we conduct an ablation study on the optimized softmax function in the attention layer. We address training instabilities from the traditional softmax function by replacing the exponential nonlinearity with the JLU function, which improves performance on the ImageNet classification benchmark. We also switch from L1 normalization to L2 normalization, leading to further performance gains. These changes help our model achieve performance parity with the standard vision transformer. Additionally, we modify the transformer's layer normalization to a non-parametric version by removing its trainable weights and biases. This ensures that only key value parameters are learned, and our empirical results show that the model maintains comparable performance after this adjustment. Section Summary. In this section, we evaluate our proposed architecture's performance in language and visual modeling tasks, demonstrating its competitive expressiveness against standard transformer models. We also discuss our model's efficient scaling capabilities, which allow for increased parameter size without escalating computational costs, and highlight improvements made through optimized softmax functions and non-parametric layer normalization. Section: Future Work. In this section, we explore future work by extending the mixture of experts paradigm. We view Tokenformer as a unique version of the mixture of experts framework, where each key value pair acts as a separate expert. This design can greatly lower the computational costs linked to interactions between tokens and parameters. Moreover, Tokenformer's ability to adjust its computational load for token interactions enhances its efficiency, paving the way for more resource-friendly foundational models. We also focus on advancing parameter-efficient tuning. Tokenformer's method of adding more key value pairs illustrates a way to tune parameters efficiently. When faced with new tasks or datasets, the model can quickly adapt by adding these new parameter tokens to its existing pre-trained parameters. Additionally, we aim to integrate vision and language models. By utilizing Tokenformer's tuning capabilities, we can merge key value tokens from both visual and language tokenformers into one set. This allows us to introduce new learnable tokens for aligning vision and language tasks. In terms of device-cloud collaboration, Tokenformer can act as a knowledge base on the cloud side for on-device large language models. Each key value pair represents a learnable pattern, enabling real-time processing on devices while offloading more demanding tasks to the cloud. Finally, we highlight the importance of enhancing model interpretability. Since Tokenformer relies entirely on attention mechanisms, it naturally benefits from the interpretability that comes with attention in token parameter interactions. This feature improves the model's explainability, supporting the AI community's goal of creating more transparent and understandable models.